We've had various speakers, architects, quantity surveyors, civil engineers and so on. I suppose I qualify as an engineer posing as an academic. We had a presentation last year which dealt with anthropogenic impact, and it dealt just with CO2 and global warming, and it just touched on biodiversity. And I sat there thinking, it's a much bigger thing than that. So that was why I ventured to offer a contribution myself this year. Going back to beginning, if you burn hydrocarbon fuels in air, you get CO2 and water vapour which pass into the atmosphere. Going back sort of to the end of the Victorian era, Swedish chemist Svante Arrhenius said that if we continued to burn coal like we were doing, we'd get CO2, extra CO2 in the atmosphere, we'd get global warming. At the time, of course, probably about 90% of the world's population lived in the northern hemisphere, and industrialisation was spreading from Europe westwards to America, eastwards to Russia and Japan. Moving onwards to the present century, another Swede, Jan Rockström, at the Stockholm Resilience Centre, got a group of people together, including people like Will Steffen and Paul Crutzen, and they looked into the impacts that we're having and the main areas where there are concerns there might be some overall boundaries that we're approaching and that we're in danger of crossing. They've identified 9 areas, and those are they. And as I say, last year somebody talked about that and just mentioned this. Now it's a big list, and I'm not going to crunch through the whole thing. I've written the paper, and I say a little bit about each one in the paper. But looking at, first of all, the climate change business, CO2. It's not just the atmosphere that warms up. The world's oceans also absorb energy. In fact, the thermal capacity of the oceans is about 1,000 times greater than the Earth's atmosphere. And I read somewhere, climatologists, oceanographers are saying that now the upper 600 or 700 metres of the world's oceans are now 0.3 of a degree C, 0.3 Celsius, warmer than they were due to climate change. That doesn't sound very much. So I thought, well, how much is it? So I did a quick sort of 4 pi r squared, put in the Earth's radius in meters, got an area, multiplied it by 0.7 because just 70% of the world's covered with water. That's a volume, an area. Multiply that by the depth, 600 meters, that gives me a volume. Multiplied that by the density to give a mass. And then I multiplied that by the specific heat capacity of water. And that tells me how much energy it takes to warm the whole lot up by 1 degree C. So I multiply that by 0.3 for the 0.3 degrees. And obviously I got an astronomical sort of number. And well, how much is that? What will that do? Well, in a former life I was a metallurgist, and I thought, steel. How much steel could you make with that? At the moment we make about 1.6 billion tonnes, 1,600 million, and it takes, in a modern efficient steel plant, it takes about 12.5 gigajoules of energy to make 1 tonne. So I multiplied those two together and got another big number. Divided that number into the first one to find out how many years worth of steel you could make, and the answer came out at 15,000 years, which is non-trivial. I'm sure you'll agree. That CO2 doesn't just remain in the atmosphere, it dissolves in seawater. Now, going back to school chemistry, acids are proton donors. Protons are hydrogen ions, so we can measure acidification by measuring the pH. And again, something I saw in a book or a paper, because of acidification, the pH of the world's oceans has gone down from 8.2 to 8.1. Man in the street, well, that's not much, that's only just over 1%. But of course, pH is measured this way. That's the hydrogen ion concentration. It's actually a logarithmic scale, so the pH is log to the base 10 of 1 over H plus. When that goes up, this goes down. So 8.2 to 8.1. And remember, because it's a log, it's got two parts. The first bit is an integer, which measures the order of magnitude. The second bit behind the decimal point is the mantissa, and that's actually a real number, which encodes the scale between 1 and 10 of the thing you're getting the logarithm on. So if you consult your log tables or your slide rules, if you've still got one, you probably haven't, you'll find that 0.2 down to 0.1 isn't 50%, it's 30%. So what it means is the acidity of the oceans has gone up by 30%. Well, if you're a fish or a crustacean or anything that's trying to live down there, that's not really very good news. So what we've got then is warmer seas and more acidic seas. And if we go back to our, we've got a lot of different life forms on this planet, and since 70% of the world is covered with seawater, a huge amount of the biodiversity on the planet actually lives in the seas. So that's really sort of bad news in terms of biodiversity reduction. That's the other item there, biodiversity. So that's linked to that, and they're both linked to this. Under the sea, just as there are on land, there are what we call biodiversity hotspots, areas where the numbers of different species per square metre or per hectare are really very high compared with most places on average. Because on land, the biodiverse hotspots are things like the Amazon rainforest and the rainforests in Indonesia. And under the sea, the hotspots are things like coral reefs. You've all seen the pictures of the Great Barrier Reef, I'm sure, where you've got all these wonderful coral structures with these multicoloured plants growing and these shoals of fish of all sizes, shapes and colours swimming around, and it looks absolutely beautiful. And it is. Now, you may also more recently have seen pictures of coral that's beginning to suffer the effects of warmer seas and more acid seas, and you'll know that the coral, all its colour is lost. The coral assumes a ghostly sort of off-white appearance. It doesn't die immediately, it can take a few years, but it's on the way out. Now, all of these areas of impact are all interconnected when you get down to it. And what it comes down to is that anthropogenic impact now has acquired the status, if you like, of a force of nature. It's a major impact, to the point where people are beginning to wonder how much longer we can go on. I read a book by Lord Rees of Ludlow back in 2000 where he was speculating about the chances of Homo sapiens making it beyond the end of the 21st century. The Dean who welcomed us this morning spoke about the urgency of moves towards more sustainability, and he was quite right. People have begun to speculate that we may be entering another mass extinction, and you may be aware that there have been a number of mass extinction events. Before 600 million years ago, life was pretty simple, and we didn't find much in the way of complex structures. In fact, for the first billion years after life started, the atmosphere contained little or no oxygen. The great oxygenation event occurred about 2,000 million years ago, and the oxygen content has risen. It's actually been higher than it is now, but it's now around, as we know, about 21%. So looking back, there have been 5 mass extinction events. 2 of them are particularly well known, perhaps. The biggest one of all was the Permian Extinction. It's called the Permian Extinction because the rocks where they found the evidence were found in a mountain near Perm in Russia. One of the most famous ones, of course, is this one, the famous KT event, which was caused by a meteorite impact. All these were volcanic events. The Permian extinction, what happened was a huge fissure opened up in Siberia, and molten lava spewed out of that for not a year or a decade or a century or a millennium. It probably wasn't continuous spewing forth, but it went on and off for possibly as long as 1 million years, so that at the end something like 60 or 70 million cubic kilometers of lava formed a huge igneous province in Siberia. Now, it wasn't just the lava that spewed out, it was carbon dioxide, it was oxides of sulfur and nitrogen, it was particulate materials. People have already spoken about particulates. They are very important, and they're included on the Rockstrom list as aerosol particles. And one thing you notice about these 5 major events, they were such massive affairs that they actually triggered a change in the geological era. At each stage we triggered the Permian to Triassic, and then the Cretaceous to Tertiary was done with the impact of the meteorite. There has been some recent work done by Steve Gollick, University of Austin, and Joanne Morgan from Imperial College in London, and they've raised enough money to drill down into the Earth's crust at the site of the asteroid, the meteorite impact, and look for the evidence of what went on. I did some sums on this a few years ago, and I pulled a file out again, and it's now thought this thing's a bit bigger than when I did the sums, so I rejigged the calculation and treated it like terminal ballistics, and how much energy do you dissipate, and again an astronomical number. Well, how much is that? It was all in yottajoules. A yottajoule is a million joules, big number. Now, sunlight arrives at the surface of the Earth at the rate of 1 petajoule per second, all over. So I thought, right, 1 petajoule per second, how much would arrive in here? So again, I did a calculation and got another big number. And the energy that was dissipated when that thing hit, turns out it was equivalent to 4 months solar radiation for the whole Earth, arriving in 4 microseconds. Wham! So of course, you know, big effect. Life, all the biosystems on Earth are what complexity theorists are fond of calling complex adaptive systems. They can respond to change. Well, if it's a slow change, yeah, they might be able to start. But if it goes on and on for nearly 1 million years, forget it. It eventually becomes overwhelmed. And of course, if it's a really rapid event like that, it's curtains anyway. If it's big enough, it has to be big enough, and that amount of energy was big enough. It blew up millions of tons of particulates and obscured the sun, and the dinosaurs, most of them, died out. A few, crocodiles, alligators and caimans, are survivors from that era. And they survived because they could lie underwater and they didn't need to eat anything for 6 or 8 months. So they were all right. But the big lads walking around on the surface, they all went extinct. Now, the question is, the totality of anthropogenic impact, how big is it? We're doing it perhaps slower than the volcanism, but nowhere near as quick as the meteorites. And that's the thing that interests me at the moment. That's the thing that I'm devoting a certain amount of time to looking at. I've got some thermodynamicist friends. I'll be going to talk to them and pick their brains. I've got some ideas. So the whole business of our impact is no. These are all the areas. Some of you have referred to those various combinations of them. They're all crucially important, and I've tried to show they are all interlinked. That's really the summation of what I want to say. Thank you very much for your attention.